So hello everybody. I see you are 17. Maybe we can start. And first of all, thank you very much for answering the questions. And there were only 13 of you who answered, so this is a bit disappointing. There is still half of you who don't answer questions, and it's I really would like to know why. Is it difficult or tedious or annoying? But I sincerely hope that for the next pair of questions, there will be more of you answering. Okay, so let us look at the answers, which are quite interesting. So the first question was about deterministic and non-deterministic automata. And I got 1, 2, 3, 4 kinds of answers. I got answers in which the definition is given, but you don't really answer the question. So this is the case of Ben Gabrit and Carreno Avila. So Ben Gabrit says that non-deterministic automata allow minimizing the number of parameters. Okay, but is this the reason why we should have non-deterministic automata? It's not really, it doesn't show whether it's useful or not. Then I got answers which were partly wrong. And this may be interesting to check. So, for example, Famchamp says that non-deterministic automata accept more complicated class of languages. Well, this is not true. Finite-state automata, whether they are deterministic or not, accept exactly the same class of languages called regular languages. So there isn't a single language which can be described, recognized by a non-deterministic and not by a deterministic. Okay, so it's exactly the same class of languages. And Liang says language is dynamic. We can determine the following letter by a given letter. In this case, we have to use non-deterministic automata. And a similar answer I got by Subramani, who says that there is randomness in non-deterministic automata. Well, you shouldn't consider them in this way. It's not a randomness in the sense that we are moving from state to state in a completely random way. No. Non-deterministic automata are not random. They just allow more choices. And when you want to recognize a word, sometimes you can follow different paths. So you can have many paths for the same word. But this doesn't mean that anything is random. Your choices are not random. They are well considered in order to recognize a word. Okay, so these are answers which were partially wrong, but this is very good because it allows me to give a clearer definition of the notion of finite state automata. Then I got some answers which are half the way to be what I wanted. So, for example, Makur says that deterministic automata are more complex. And he says, it can be easier to build a language in a simple way. Okay, so building in the sense that a human wants to describe a language. This is how I understand the building a language. And similarly, for example, Moreno says it could be shorter and faster to make a non-deterministic automata. Okay, so once again, it's the human point of view. And then I had answers which are exactly what I expected as complete answer by Tissot and Van der Berg. Tissot speaks about visualization, and Vanessa speaks about representation easier to understand. This is what I expected. So we need non-deterministic automata for humans. So this is the human factor. A machine doesn't care, and a machine will run faster if the automaton is deterministic. It will be the same languages which will be recognized with either one of the two cases. The machine will have less backtrack, so less bad choices having to go back and make and choose a different path. So it will be quicker for the machine, but the complexity of the automaton doesn't change anything for the machine. But for humans, there will be a big difference. So non-deterministic automata still exist today because they are easier to understand and to build by humans. My second question, the Yoda language, was not an innocent question. I asked it because I wanted to introduce a notion, and I wanted to have your opinion before introducing this notion. And most of you have answered correctly that it doesn't change the way we perceive the world. Now, this is correct, but it's not the entire truth. I got an answer by Liang. Liang says in Japanese and in many other languages, the syntax is subject, object, verb. Okay. So they may have a different feeling of an action. Okay. So this is one step further. And the answers which I really appreciate are the one by Supramani and Tissot, once again Tissot. Supramani says that what is important is prioritization. The way the sentence is framed is a choice of priority. Yoda wants to emphasize truly wonderful more than the mind of a child is. And Tissot says also that we can have nuance and words which are emphasized and accentuated. And this is going a bit farther than the fact that the cognition doesn't really change with language, but sometimes the order of words can change emphasis, can change the part of the sentence we want to emphasize. And languages that have a strict order have more difficulties in emphasizing. So in French, you have a strict order, sujet, verb, complement, and it's more difficult. You need more periphrastic methods to emphasize. While in Japanese, you can put the subject or any complement first, and the verb is at the end. And depending on the one you want to emphasize, you will put it first, either the subject or some of the complements. And the same happens in Greek or in Russian, where the order of words is flexible. Now, yes? Okay. The fact of having a flexible order needs extra constraints in grammar. So in Greek and Russian, you have case, nominative, genitive, accusative, and so on. This is extra difficulty in grammar, but it allows you, and the same thing in Arabic, it allows you to have a flexible order, and with a flexible order, you can emphasize easier specific parts of your sentence. Okay, so thank you very much for answering. Now, the second question, I asked to introduce the notion of linguistic relativity, also known as the Sapir-Whorf hypothesis. So let me show you the Wikipedia page. So the Sapir-Whorf hypothesis is an ideology from the beginning of the 20th century, saying that the way the language we use determines the way we perceive the world. So this was a very strong hypothesis. And then later on, there was a weaker version saying that it's not deterministic, it just influences the way we think and decide and so on. And this hypothesis was refuted later on by Chomsky with the theory we will see today, the generative grammar by Chomsky. And of course, there were political reasons, and this was an ideology of the beginning of the 20th century, which was quite influential. And this was the background of the question I asked. Okay, so let us start today's lecture. So today it's again the linguistic slot. So last time, 2 weeks ago, we saw phonemics, graphemics, morphology. I will very quickly show you some slides from the morphology section. So what is important for what we are going to do today? The definition of morpheme. What is a morpheme? It's a minimal unit of meaning. You have free morphemes and bound morphemes. So free morphemes are the many words you have in a language. And bound morphemes are affixes, so prefixes, suffixes, and so on, that are added to free morphemes to modify some characteristic. So for example, for conjugation of verbs, for the plural of nouns, and so on. So this S here is a bound morpheme, while table is a free morpheme. Out of a free morpheme, by adding bound morphemes, you can have many cases, many forms. So this is the study of forms. Form is a Latin word. The Greek word for form is morphe. That's why we call it morphology. It's the study of forms. When it's the same word which is declined or conjugated. We call this inflectional morphology. And as you see, depending on the language, you have many, many methods of obtaining new forms. And then when we create new words derived from existing words, this is called derivational morphology. And again, we have methods which are more or less standard. For example, the suffix able, being able of doing something, manger, mangeable, faire, faisable, prefixing, composition, and so on. So this is derivational morphology. Of course, this can be automatized more or less. One way of modeling either inflectional or derivational morphology is through finite-state automata. So this is an application of finite-state automata. And at the end of the last lecture, I gave you the example of Arabic, which is really very irregular in terms of morphology. It has two perpendicular notions, the notion of root and the notion of scheme. Root is the semantic part. It's a set of 2, 3, or 4 letters. And these letters define a domain. For example, kataba, the domain of writing, fa'ala, the domain of action, qaraba, the domain of proximity, and so on. And these letters are combined with schemes, and schemes are combinations of either short vowels or absence of vowel or even consonants. And by combining roots and schemes, you obtain thousands and thousands of forms. So it's a very mathematical approach to morphology. Now, this is now new territory. Another way of deriving words is by composing them. So in some languages, we have an intermediate between the word and the sentence. This intermediate, which is also what in syntax we consider as a noun phrase, a group nominal, is the compound word. So which languages use a lot of compound words? German, Dutch, Russian, Welsh. So in general, languages which are known for having very long words. So for example, in German, this is a single word, Wahrscheinlichkeitstheorienstreit, which means the dispute, Streit, on theories of relativity. And when we study morphologically this word, we see that we have a tree, a hierarchical tree, where you have the first component, Wahrscheinlichkeit, which is relativity, which again is a compound word with different parts. Wahrschein are free morphemes, Lichkeit, S are bound morphemes. Then the second component, theory, free morpheme, suffix N, bound component, Streit, the dispute, again, a free morpheme. Now, what is interesting is that there have been studies on the speed of typing on a keyboard. And it has been shown experimentally that when typing German on a keyboard, there are many pauses between the keys that depend on the position on this tree. So, for example, between kites and theorem, you see that the S of kites is here, quite low. And then to get to theory, you have to go up, 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 and then down again. So this distance in the tree is correlated with the nanopause when typing the word on the keyboard. So, and this means that somehow the brain has stored the information in this way. So this is a work done in the domain of psycholinguistics. We have the same phenomenon in Japanese. So this again is a single word with many kanji, with many Chinese characters. And again, it has a structure. And there's a project I wanted to realize last year, but because of the COVID pandemics, I was not able to do it experimentally, to show that here again, we have nanopauses, not when typing on the keyboard, because typing Chinese characters on the keyboard depends on many things. You have input methods and the method learns your habits, but when drawing the characters. So my hypothesis is that when this character is drawn, depending on the position on this tree, you have small pauses between the characters. This is something we will either show or refute. Okay, now we move from morphology to another very important discipline called terminology. And it's especially important for you, engineers, because in your projects on natural language processing, you will very probably have to deal with knowledge from companies, from domains of knowledge, domains of activity. And in these knowledge domains, it is important to have terminology. So if you're going to work, for example, in the domain of travel, then you need a good knowledge of terms concerning traveling. So travel means, travel regulations, travel habits, travel budgets, whatever, tourism, and so on. If you are going to work in some other domain, again, there will be the terminology of the domain, and processing data in a specific domain means also recognizing terms. Here you have an example, White House travel office staff. We call this a term, White House travel office staff, and we call it a complex term because it has many words. Now, inside this term, you have subterms. For example, White House is a term. White House is a term because it's not just a house that is white. It's in fact a named entity. It's a very specific house in the concrete meaning of the word, but it's also an institution. It's also a place, the place where the President of the United States lives, and so on. So these two words become a term, and this term happens to be also a named entity. But if you look at travel office, this is not a named entity, it's simply a term. But why is it a term? Because we often find these two words together with a specific meaning. A travel office is a place where we can buy tickets, where we can get recommendation, and so on. So we do say travel office. We don't say travel bureau. We don't say travel desk. Or maybe we say it, but less frequently. So this is also a term. And by combining White House and travel office, we get White House travel office, which is a specific travel office. And this can again be considered as a term. And the staff of the White House travel office can also be considered as a term. So what is a term? A term is the linguistic representation of a concept inside a domain of knowledge, a domain of activity, and so on. In other words, a term is something unambiguous with a specific meaning in a given domain. The same word or the same group of words in a different context may not be a term, or may be a term with a different meaning. But in a specific domain, we have terms. So for example, in mathematics, you have the term of number, integer, decimal, rational, real. You have the concept of set, empty set. So empty set is a term. The set of real numbers, the set of complex numbers, all of these are notions, and these notions are represented by terms. A simple term is a single word. A complex term contains more than one word. And the discipline of terminology studies terms. It studies not only their meaning, but also their lifespan. Because a term is like a living organism. It gets born, and then it evolves, and eventually it dies. So, for example, the term téléphone portable. This term was born in an unofficial way, because the official term for a portable, a mobile telephone was téléphone mobile. But this term was not used by people. Instead, people used téléphone portable. So the complex term téléphone portable was born. But at some time, and this can be located in time, it can be studied, people started using portable without telephone. So at the beginning, where there were not many portable phones, mobile phones, you had to say téléphone portable, because otherwise portable would be either not understood or misunderstood as a laptop. But when mobile phones became very popular, telephone was not necessary anymore, and téléphone portable became portable. And maybe someday, if there are no mobile phones anymore, the term portable will die. Okay. Now, question, why is téléphone rouge a complex term, but not téléphone jaune? Téléphone jaune is just a telephone which happens to be yellow. So the fact of being yellow doesn't add any more information. It's just a change of color, a color among many colors. Téléphone rouge is a specific telephone. Historically, it was the telephone between the White House and the Kremlin. And if you look into Wikipedia, you will see that this was never read, in fact. It wasn't even a telephone, it was a telex. Anyway, in popular knowledge is that there was a red telephone, and in many movies you can see a red telephone. So this is a term because it means more than just a telephone that happens to be red. Now, the question is, how can the machine detect terms? On this, there has been a fundamental work by Franzi and Ananiadou defining the property of termhood, so in French, termitude. And termhood is a value, a numeric value, we calculate on groups of words. And this depends on the subgroups and the supergroups. Now, you will see the formula this afternoon. So this afternoon, we will have a lab in which we are going to work, among other things, on termhood. And this is very important because if in your internship or later in your work, a company asks you to process a corpus of data, then one of the first things to do is to detect terms and to validate these terms with experts in the company, and this becomes the intellectual heritage of the company. Okay, so I will not give you the formula right now. I will just give you an example. Let us take représentation en virgule flottante. So this is a term. It has the pattern noun, représentation, en, preposition, virgule, another noun, flottante, adjective. So virgule flottante is a noun phrase. En virgule flottante is a prepositional phrase. And so now I have a noun followed by a prepositional phrase. This is a pattern that is commonly, that can be a term. So it's a potential term. Now, is it a term? I look at the frequency of this term in a corpus. This corpus can be Wikipedia or a book on computer science and so on. I will find very often représentation virgule flottante. I will never find a représentation virgule. It will always be followed by flottante because représentation virgule doesn't mean anything. So if I compare représentation virgule flottante with the sub-terms, sub-candidates, well, this one, représentation virgule, has frequency 0. Now, what are the super terms? Imagine that in a sentence, I say représentation virgule flottante obtenue. Nous allons considérer la représentation virgule flottante obtenue par cet algorithme. Now, the adjective obtenu occurs once or twice, but very rarely after représentation virgule flottante. So obtenu is accidental. If I look at the frequency of représentation virgule flottante obtenue, it is very low compared to the frequency of représentation virgule flottante. So for this reason, the algorithm given by Franzi and Ananiadou will say représentation virgule flottante has a high degree of termhood, while both représentation virgule and représentation virgule flottante obtenue will have a low degree of termhood. So more about terminology this afternoon. The next very important notion is the one of part of speech. So this is something you learned in school, that words can be nouns, adjective, adverbs, articles, conjunctions, interjections, prepositions, and verbs. There may be more parts of speech depending on the language, but these are the basic ones. And they don't exist in all languages. For example, in Arabic, there are no adjectives. We have only nouns. These are the most frequent part of speech for French or English. To study them, to detect them, to describe them, different tools have different sets of tags. This is a tool called tree tagger. It's a morphological parser. So it will give the part of speech of words in many languages. It has been trained in many languages. And here is the set of tags you get for French. So these are the tags used by tree tagger. As you see, you have abbreviations, adjectives, adverbs. In the case of determinants, you have two kinds. You have articles and possessive pronouns. Then you have proper nouns, numerals, different kinds of pronouns. And for each tag of verb, you have a subtag given either the tense or the mode, and so on. There are other sets of tags. They are called tag sets. And one that is very frequently used is the pen tree bank tag set. And there are others. These tools we are going to use this afternoon, depending on the language, on the type of text, and on the type of language, the register of language, they can be very accurate or they can give very bad results. So that's very variable. And it depends also on the way they have been trained. All of these pieces of software we will see are trained on corpora that have already been tagged. So mostly by humans. So you have the so-called golden corpora, where tags have been given by experts, by human experts. And these are not very large corpora, but we know that they are very precise and very correct. And then you have other corpora that have been developed out of these tools with some sporadic verifications, and these are less precise. So depending on the corpus you use, the tool will be more or less precise, more or less detailed, and this is why there are many parsers, and they can be trained on many different corpora. This is also something we will see this afternoon. And this closes the chapter of morphology. So morphology is inflectional, derivational, and we deal with parts of speech. We detect the part of speech. Now, the next section is about syntax. Syntax is the meaning that is hidden in the order of words. So in French, it's very clear that depending on the order of words, the meaning can change completely. Between le chien a mordu la fille and la fille a mordu le chien, the meaning is completely different, even though you use the same words. In other languages, the order is more flexible. And in that case, we combine the order with some other phenomena called case to provide the information on the meaning of the sentence. Now, the question is, how do we describe syntax? What is syntax? How can we define it? There have been many theories. The first very important theory is the one of generative grammar by Noam Chomsky in the 50s. So Chomsky was the one who introduced formal grammars. So you see that his contribution is very important, not only to linguistics, but also to computer science. And his theory goes well beyond the description of syntax. His theory is more generally about how humans learn language, how they learn and how they use language. So he's saying that there is a part in the brain, in the human brain, that allows us to learn syntax. And this is at the age of 3. So earlier, we don't have any notion of syntax, we barely speak. And later, we have more difficulty in learning syntax because that part of the brain is used by other functions. And for example, because of this phenomenon, you have languages that are learned by first generation and second generation of migrants. And on the first generation, so people who arrive in a country and have already their own language, and they learn the language of the new place of living as a second language, they will build something new, some kind of merge of the previous and the new language, but this merge that is called a pidgin will not have real syntax. It will be a mixture of syntax of the first and of the second language, while their children will learn this new mixture and with a new syntax. And this is called Creole. So Creole is a mix of languages that has survived one or more generations, that has native users and has a complete syntax and sometimes a new syntax. Okay, now Chomsky says that syntax can be described by formal grammars, the concept we saw last week, and whatever can be obtained by derivation rules is correct. And this is something we do subconsciously. So he says that our brain is able to recognize a sentence as being correct even though it's the first time we see that sentence. And he says that there is an infinite amount of possible sentences, syntactically correct, not semantically, but syntactically correct, and that we are able to immediately recognize whether they are syntactically correct or not, whether they respect rules of a formal grammar or not. The theory given by Chomsky is called syntax by constituents. So what is a constituent? Constituent is a part of a syntax tree. It's also called a phrase in French, group. So be careful because there is difference in meaning of the word phrase. In French, phrase, la phrase, means sentence. It's a complete sentence. In English, a phrase is part of a sentence. So English phrase is a French group. Group nominal, group verbal is noun phrase, verbal phrase. Okay. You see a syntax tree, la fille mange la pomme. The first level of the tree is the one of part of speech, determinant, noun, verb, determinant, noun. And then when we go up, we go through different levels that are constituents, noun phrases, verbal phrases, and we end up at the root of the tree, S, which is the complete sentence. So the idea of Chomsky is to say syntax can be described by a tree in which leaves are words. The first level above leaves are parts of speech. So we call this level the lexical level. And then we go up using constituents. So we have these abstract nodes that exist only to bring together parts of the sentence and say that this part of the sentence has a common characteristic of being a noun phrase, a verbal phrase, and so on. Now, every phrase, so every constituent, has a head, and the head gives the name of the phrase. So, for example, a noun phrase like la fille has a noun, that is the head. A verb phrase has a verb, mange, that is the head, and so on. And we have prepositional phrases, adjectival phrases, adverbial phrases, and so on. In French, we have many kinds of phrases. This is something we have learned in secondary school, college. There is a Becherel on grammar that explains all of that. And here are the different kinds, the most important kinds of phrases. Noun phrases, adjectival phrases, verbal phrases. Now, verbal phrases have complements, and the number of complements is called the valency of a verb. So, for example, a verb with valency 0 is an intransitive verb. To sleep is a verb with valency 0. Then you have verbs with valency 1 that take only a direct object, complement objet direct, verbs with valency 2, and so on. And here's another example of a sentence with a subphrase, a relative subphrase. La fille mange la pomme qu'elle a achetée hier. The order of words, as we saw in the question, is really very variable, and it's language invariant. In a given language, you have a given order, except for languages in which this order is flexible. Now, most of the world languages are subject, object, verb. So this is not the number of speakers. This is the percentage and the number of languages. So in these languages, you have languages with very few speakers. And in these cases, you put the subject first and then the object in a different case. Here you have ophilos, nominative, ton philon, accusative, enkindinis, dative, ignoski, verb. Now, almost the same amount of languages are subject, verb, object, like in French. La fille mange la pomme, so subject, verb, object. It's the same in Chinese, Italian, Spanish, so all Romance languages and so on. Then you have a small amount of languages that put the verb first and then the subject. So this is the case of classical Arabic. Yaktubu, al-katibu, so nominative, writes the author, al-kitaba, accusative, the book, so writes the author of the book, and also Irish, Tagalog, and so on. And then a very small percentage are verb, object, subject. Because it's natural to prioritize the subject rather than the object. So in these languages, really the subject is last. And then you have languages in which the order is flexible, and these languages allow emphasizing any part of the sentence. In computing, you have the inverse Polish notation, which is used by some low-level languages like PostScript, that is of kind SOV. So for example, in PostScript, when you write 3, 4, 5, then these 3 values are put on a stack. And then add is an operator which will take 2 elements from the stack, sum them, and return the result on the stack. So after add, on the first level of the stack, you will have 9, and then on the second level, 3. And then 3, 9 div will be division of the first level of the stack by the second level, and so the result is 3. Okay, so these are the production rules we saw last week. So last week we saw them in a general complex of formalizing different situations. Here is the specific context of grammar. And when I say grammar, I mean both morphology and syntax. And here are some examples. So for example, here there's an error, there should be an S. So S is noun phrase followed by verb phrase. This is typical in French and English. And then a noun phrase can be a determinant. Noun phrase is necessarily a determinant, followed potentially by 0, 1 or more adjectives, by a noun, a single noun. Again, 0, 1 or more adjectives, because in French you can put adjectives on both sides, and eventually a relative subphrase. A verbal phrase will be a verb followed by a noun phrase. As you see, this again means that this verb is of valency at least 1. So this won't work with intransitive verbs like sleep and so on. As you see, we can write many production rules, and using these rules we can derive sentences, and sentences that are derived using these rules will be correct sentences. And the difficulty, like we said last week, the difficulty is not just to obtain all correct sentences, but also to be able to refute incorrect sentences. So we want precision and recall. Recall will be to obtain all possible sentences, and precision will be to block, to invalidate sentences that are not correct. Obtaining these rules for a given language is an operation called grammatical inference. So grammatical inference is like a data mining mechanism. You take a corpus in a language, and there are different algorithms allowing to write rules, to test those rules, to refine them, and progressively to obtain a better coverage, both of the grammatical and the ungrammatical sentences of this language, of the corpus. So when will we use grammatical inference? Whenever we think that there is a structure, there is a syntactic structure in some corpus. If it's natural language, then it always has a syntax. If it's some other kind of data, then maybe we can consider it as either a formal or a controlled language and try to describe its syntax. So, for example, we have a project with Tian on studying the maintenance reports of a factory in Alsace, electricity production factory. And there are maintenance teams, 3 teams, so every 8 hours they change around the clock. And so every day we have 3 reports on the condition of the elements of the factory. And of course, since this is the same every day, and they are in a hurry and they want to be precise, they have developed a style which is repetitive, short, and a bit cryptic also. So is this natural language? Not anymore. It's a kind of controlled language because it's written under constraints. And we can study this as a controlled language, and we are applying grammatical inference on it to obtain the grammar of this very specific kind of language used by the maintenance teams of this factory. And our goal in studying it is to be able to predict anomalies, because we also have data on the factory, performance, we have sensors, we get the data captured by these sensors, and we will correlate the data with meaning extracted from these reports, and we hope to be able to predict anomalies. Okay, so this was a small parenthesis to emphasize the importance of grammatical inference as an operation. So in machine learning, we often recognize frequent patterns. For example, in transactions, you have items, and these items form patterns. When you go in a supermarket, you will buy specific products, and these products you choose are patterns, and data mining will study these patterns, and the geography, the disposition of products in the market will be according to the most frequent patterns to make shopping easier. So this is something which is known ever since the 80s. It's the heart of data mining. In the case of grammatical inference, we go further. It's not just frequent patterns, it's really rules, formal grammar rules that are studied and give a much better understanding of phenomena. So let me go on. Up to now, the examples we have seen are those of standard grammar as we learned it in school. Constituents, verb phrases, noun phrases, part of speech tags, and words. Now we will go further. We will try to refine, extend this classical grammar in order to solve some problems. So the first notion we give to go beyond the grammar we learned in school is the notion of dominance. We will say that a node of the syntax tree, dominates some other node when it is its ancestor. So for example, not P, but NP, here's an error, NP dominates phi, since it's its ancestor. And it immediately dominates if it is its parent. So NP immediately dominates N. We also say that a node exhaustively dominates some terminal nodes when it is their common ancestor. So for example, VP dominates pomme, dominates la, dominates mange, but exhaustively dominates mange la pomme. What is a constituent? So a constituent is a set of terminals that is exhaustively dominated by the same node. So in more common terms, a constituent is the leaves of a branch. So take any branch of the tree, take the leaves of this branch, you have a constituent. Okay. So one way of saying this is that they are exhaustively dominated by the same node. Okay, and this shows us some very important facts about syntax trees. So something you should think about is the fact that a syntax tree has an order. It is the order of words. This is the horizontal order, the syntagmatic order. And it also has an order between the root and the leaves. And you can combine these two orders to get a traversal order of the tree, which is going from the top, so from the root downwards, and then up again, and following the horizontal order of the leaves. So for example, I start by S, N, P, det, la, and then up again, and then down, N, fille, up again, up again, down, VP, down, V, mange, up again, VP, NP prime, det prime, la, up, and NP, pomme, and I'm done. So this is the unique traversal order of the tree, and it's unique. It's the only one that is compatible both with the fact that S is the root and the fact that words have an order. La, fille, mange, la, pomme. And constituents are always contiguous. Okay, you cannot have fille, la, pomme being a constituent, because branches of the tree are compatible with the order, the horizontal order of words. Now, we have another notion, and notions now will become more and more complex. The notion of C command, C like constituent. So C command is a state. A node C commands some other nodes when we have two conditions. First of all, they are not descendants. So C command is always between two different branches. And they have the same ancestors. So, for example, V, given in red, C commands all the nodes given in green, because V and NP prime have the same ancestors, namely VP and S. And V is not an ancestor of NP prime, det prime, la, N prime, pomme. Okay, so it's not necessarily in one sense. It's symmetric. So for example, NP prime, C commands V and mange. Since NP prime and V have the same ancestors, and they are not, and NP prime is not an ancestor of V. Okay, so C commandment is looks always like this. You have two brother or sibling nodes, and the one C commands the branch of the other. Now, why do we introduce these notions of C command and of dominance? Because we want to solve a problem related with references. So this is something we will see this afternoon in the lab. An important phenomenon when we process text is to detect and to solve references. So here are the definitions. An R expression, so this is a term for saying a reference expression. So an R expression is a noun phrase that refers to an entity of the world. Okay, so when it is a named entity, then it's necessarily an R expression. So if I say Irene, Irene is a name, so it's a named entity. So I'm referring to somebody in the world, either the real world or an imaginary world. But in the sentence, Irene sent a mail to me, it's not only Irene, mail is also an R expression, even though it's not a named entity, but it does refer to something in the real world, a mail, a given mail. And me also is an expression since it's referring to me, the narrator. Okay, now what we call anaphora is a noun phrase that refers to another noun phrase of the text. So, for example, in the same sentence, when I say Irene sent a letter to herself, herself is an anaphora of Irene. Irene is the antecedent of herself. Okay. And you see that in this sentence, Irene and herself are bound together. You cannot use herself without specifying who you are talking about. We are talking about antecedent when the referent is before the R expression, before the anaphora. So Irene is before herself. It may also happen that the referent is after the anaphora. In that case, we call it a cataphora and not an anaphora. Okay. Now, a pronoun is also a noun phrase that can or not refer to another noun phrase in the text. So when we say Irene said she likes Paul, she is a pronoun, but we don't know whether this she refers to Irene or to somebody else. The only thing we know is that she refers to some feminine person, female person, but we don't know if it's Irene or somebody else. We have a notation on specifying referents and anaphoras and pronouns. So here I'm writing Irene with an index I, sent a mail, J, to me. Well, me, I could also put brackets with a K. Irene sent a letter, J, to herself. And you see here, I use the same index as in Irene. While here, Irene said she likes Paul. Well, this she can be Irene, but also somebody else. So I'm using a question mark. Now you see by this notation that this is something we want the machine to do for us. Now, when two noun phrases have the same index, we will say that they are co-indexed. So here, for example, Irene and herself are necessarily co-indexed. Okay, so let us take 3 sentences, and this will be the last slide before the break. Heidi came herself to the party. Here we have clearly Heidi and herself co-indexed. The father of Heidi, you see Heidi has an index I, the father of Heidi has an index J, came himself to the party. We know that Heidi is female, is a female person. Her father is a male person. So himself means that it's necessarily the father of Heidi. So here I have a J. But when I write the father of Heidi came herself to the party, there's a problem. And the problem is not only that I'm intending the father of Heidi and using the wrong gender. What if I wanted to refer to Heidi and not to her father? Then, of course, this would be I. But is it possible to refer to Heidi at this location? No. And this is an agrammatical sentence. So this sentence is not grammatically correct. But why? So this is what we will try to find out using the concepts we introduced, concepts of dominance and C command. This is called binding theory because we bound constituents, referents, and references in French, théorie du liage. And this theory will allow us to show that the third sentence is incorrect and the other two are correct. Why do we need a new theory? Because in Chomsky's theory, there is no problem with this sentence. So if we take the production rules of English, then we can obtain both sentence number 2 and sentence number 3. So for Chomsky, Chomsky's grammar is unable to invalidate this third sentence. And the theory we will explore just after the break will allow us to validate the second sentence and invalidate the third. Okay, so let's take a break. It's 10:50. Let us start again at 11:05. So see you in a moment. Let me explain the syntax of complex tags. Here you have a simple tag. Gérard is a noun phrase. Here you have a verb, and this verb expects two things: a noun phrase on its right, and once you give it this noun phrase, you obtain a verb phrase, And this verb phrase expects a noun phrase on its left. And once you give this verb phrase a noun phrase on the left, you obtain a sentence. So here is the second part. It says, give me a noun phrase on the left. So the left is given by the backslash pointing to the left, and you will obtain a sentence. But before you need that, you need the direct object. So this part here says, give me a noun phrase on the right. So right is symbolized by the slash. And you will get this, this. And this is a verb phrase. What is a verb phrase? It's something where when you give a noun phrase on the left, you get a sentence. So this is like this tag here is like a program saying, I want two things. I want two noun phrases, one on the right, and that one I want first, and then one on the left. And once you have given me these two things, I will give you a sentence. Okay, so you must admit that this is quite elegant. We don't even use intermediate tags like verb phrase. We don't need to. We only give the inputs, noun phrases, and the output, sentence. So here we have a noun phrase, here we have a noun phrase, here we have this complex tag. And now what happens between those two? Here is an operation which is called forward application. Application like in functions. I take a function and I apply it to a value to obtain a new value. I take the sinus function, I apply it to value 90, and I get a new value 1, 90 degrees. So same thing here. I take the function s backslash np slash np, I apply it to np, and I get this. And this is again a function. Only this time I will do backward application in the sense that I am applying it to something on the left. And this is why I have a backslash here. So I apply this function to this NP, and I get a sentence. So this inverted tree says that if I start with the tag NP for Gerard, S backslash NP slash NP for loves, and NP for Alice, then doing the appropriate applications, I'm getting a sentence. So this is a valid syntax tree. For every word, this theory will provide one or more complex tags. And the machine will take these candidates and try them out to see whether a complete syntax tree can be constructed. If yes, then these are appropriate. If no, then either something is missing in the grammar or the sentence is not grammatical. Okay, so you see, this is quite different behavior than the one of Chomsky. For Chomsky, loves is just a verb. We don't know how it interacts with its contents. For combinatorial categorical grammars, loves can have many complex tags. This is one of them, and this one works. Okay. So this is forward application, and this is backward application. Here is another example. Gerard knows and loves Alice. I'm taking exactly the same tags for knows and loves. Okay? And in the middle, I have conjunction and. Here, the operation between those three is not application. It is another operation called conjunction. The rule of conjunction is take two similar tags and the conjunction in the middle and produce a single tag. So here I have S backslash NP and P, S backslash NP and P together make a single S backslash NP and P slash NP. Okay. And then I do a forward application with Alice and I get S backslash NP, and a backslash application with Gerard and I get S. So you see, this works. Let's take, okay, so this is the definition of the conjunction operation. Now, let's take Gerard loves and wants to marry Alice. Wants to marry is a prepositional phrase. So on the both sides of the conjunction and, we don't have the same type. There's a problem. For this, we introduce another operator called composition. And this operator takes something of the kind x slash y, and then y slash z, and gives x slash z. It's like composition of functions. Okay, when you compose two functions. And here is how it works. I have loves with tag s backslash np slash np. And wants has a different tag because it is followed by to marry. And I want those two together to give me the same tag as loves. This I can obtain by composition. I say that wants is slash s backslash np slash vp. To marry is vp slash np. This vp here disappears and I get this. So it's just a trick, a new operator that gives me the solution, and from there on, the rest is classical. Now, let's take the most difficult sentence. Gerard loves and Philippe hates Alice. So here is the problem. We want to obtain S. And this S has Alice, which is NP. So here we need something S slash NP to be combined with NP. And here we have a conjunction, so we need twice S slash NP to be combined with the conjunction. But how can we get from Gerard loves to S slash NP and from Philippe hates to S slash NP? This is a problem because, as you see, here you have NP, and here you have something expecting an NP on the right, not on the left. The solution here is to use an operator called type raising, montée de type. And this is a unary operator. It's applied to NP, and it replaces NP by S/S\NP. So here we take NP and replace it by this. So what's the idea? We will soon talk about lambda calculus. And in lambda calculus, this is like going from some A to lambda P, PA. P here is a predicate, something we will see next week in logic. A predicate is a function into the set true, false. So P of A is some information on A that is true or false. Lambda P PA means whenever you give me a P, I will tell you if this P is true or false. So type raising going from NP to S/S/NP is intuitively saying I replace an entity, Gerard, by the answers to all possible questions you may ask on Gerard. Okay, so I'm saying that these two are equivalent. If you think about it, it's the way artificial intelligence works. You have an entity and you can describe this entity. Describing the entity is answering to questions, and saying I have an entity or saying I have the answers to all possible questions you may ask on this entity is the same thing. And this is what we are doing. And once you do this type raising thing, you can compose and you get exactly what we want. So this is the trick that allows us to find the syntax tree of this quite strange sentence. Now, this is all I had to say about combinatory categorical grammars. The chances that you will work with combinatory categorical grammars are rather thin because they are still maybe not experimental, but not really used in industry. There are some tools. We had our PhD thesis last year on the subject on combinatory categorical grammars, but you don't have yet industrial tools on parsing combinatory categorical grammars. This may appear in a few years, but it's still in an early stage. Now I will present you another way of describing syntax, which is not only as common as Chomsky's approach, but even more frequently used than Chomsky's approach in natural language processing. And this is called dependency grammars. So dependency grammars have been defined in the 60s by a French linguist, Tenière. Unfortunately, he did this in a book that appeared after his death. This book was known only in France and it wasn't very popular. And this book was discovered by somebody in the United States at the early days of artificial intelligence. And he applied 10 years dependencies and defined what we call today dependency grammar. Now, what is dependency grammar? The idea is not to use intermediate nodes at all. So there is no such thing as constituents, phrases, noun phrases, verb phrases, all that stuff doesn't exist. We only have words of our sentence. And between words, we have relations called dependencies. With these relations, we build a tree, a rooted, directed tree. And the root of this tree is called the head of the sentence. So, for example, this sentence, which is a mixture of French and English, sorry, there should be describes. Michel describes his various aptitudes. I forgot to translate this word. The head of the sentence is the verb, describes. In most sentences, most sentences containing a verb, the head of the sentence is the verb. Dependencies go from one word to another. They build a tree, so we never have cycles. And the only word that is not dependent on any other word is the head. So you have arrows, you have a single arrow leaving every word except for the head. And you can have many entering arrows, but only a leaving one. So this is a tree structure. Here is how we represent it using a LaTeX package. And as you see here, we have this tag for saying that describes is the root. And here we have dependencies. So Michel is a dependency of describes, and every dependency has a nature, a type. So this is noun subject. Aptitudes is the object of describes. So we have a dependency between aptitudes and describes. His is the determinant of aptitudes. So his is a dependency of aptitudes, and various is also a dependency of aptitudes. Now, these types depend on the tool you're using, but there is a project called Universal Dependency that tries to standardize the types of dependencies. And once again, you have corpora annotated with dependencies, and the most important French one is called French Tree Bank, FTB, and it has 21,000 sentences annotated by humans. Here are some statistics on the French tree bank corpus. So the most frequent dependency is mod. We will see what it means. Then you have object of a prepositional phrase. So this is an indirect object. Then you have determinant, punctuation, and so on. So here are some examples taken by order of decreasing frequency in the corpus. Let's take the mod dependency. Mod means modifier, not modifier, modifier. There is an error here. And the source of this modifier can be an adjective, a preposition, and so on. So here's an example Simple is a modifier of moyen. Il y avait un moyen simple. So simple is a modifier of moyen. Simple is an adjective. Here, au is a modifier of veut. On veut au contraire. And again, there's a dependency between au and contraire. So you see, instead of taking au contraire together as constituent syntax would do, here we work with dependencies. Au is a modifier of veut, but au doesn't come alone. There is a dependency contraire of au. A modifier can also be an adverb. Ont été généralement négatives. So you see here, généralement, it's not a dependency of negative, it's a dependency of the verb était. Negative is also a dependency of était. So you see that we attach these two words to the verb était. As we also do réaction, which is the subject, and also en, which is the auxiliary. A modifier can also be a noun. Était officiellement de 1,4 million début janvier. So this is a kind of temporal complement to était. Quand est-ce qu'il était de 1,4 million? Début janvier. So this début is a noun that modifies était. And you see here the importance of the nature of the dependency. Début is certainly not the object of était. Okay, it's a complement. So for this kind of syntax description, it's a modifier. It can be a verb. So here, donner is the modifier of répit. Le répit donné. In fact, it's a participle. And in very rare cases, it can be a pronoun. Changer de nom pour adopter lui. So lui is a modifier of adopter. The second most frequent dependency is prepositional object, obj.p. So in most of the cases, 86% of cases, it's a noun. Bénéfice is the prepositional object of au bénéfice. In some cases, it's a verb, de prouver. Prouver is the prepositional object of de. The next dependencies in order of frequency is punctuation, determinants. So I don't need to give an example. Determinant is an article, for example. Then you have a dependency called dependency of compound words. Dep underline CPD. So dep CPD says that tout prix, à tout prix is an expression and tout prix is a term. And together, à tout prix forms a specific expression in locution. To show this, we attach these words together by using the dep CPD dependence. Now, a very important dependency is the subject dependency. In 59% of cases, a noun. Le rapport est. So here clearly rapport is the subject of A. So it is a noun which is dependent of A with the subject dependency. In some cases, it's a clitic, il avait. In some cases, a pronoun, and so on. Also very important is the direct object dependency, complément d'objet direct. In most cases, it's a noun. Il y avait un moyen simple, so moyen is the object of avait. And you see, this is very specific to dependency theory. The determinant always comes second. So it's not un moyen, which is the object of avait, it's moyen. Un is a determinant of moyen. Simple is a modifier of moyen. Here we have a case where the object is a verb. Il doit réunir. So réunir is the object of doit. Now, what are the roots of sentences? In 85% of cases, it's the verb. Il y avait un moyen. Avait is the head of the sentence. In a small amount of cases, 7%, it's a noun. Là-dessus, cours magistral d'économie politique, you see there is no verb in this part of the sentence. So cours is the head. And 85 plus 7 makes 92. Then there are other 8% of different heads. Now, should you use constituent or dependency grammars? Well, you will see when we start using tools, and this afternoon already we will use some tools, that most tools deal with dependency grammars. So why? Because they are less complex. You don't have any additional nodes. You only have the words of your sentence, which means that the head is somehow the most important word. And then in the periphery of the head, you have other important words. And you know the relation between the head and those words. So if, for example, you want to do sentiment mining, your client has a product, for example, Milka chocolate, so you know that Milka is a named entity you are looking for, and you get a corpus of, for example, tweets containing the named entity Milka, and you want to classify these tweets as being positive, neutral, or negative. This is a very common task. Now, at the beginning, this task was handled by purely distance. So people were saying, I look at the word Milka, if close to it, I get a positive word, then the tweet is positive. If close to it, I get a negative word, then the tweet is negative. But this is not the right approach, because this positive word may not be related to Milka, it may be related to something else. Same thing for the negative one. Or the positive word may have a negation, and the negation turns it into a negative sentiment. So to obtain a better relation between the named entity you're looking for and the surrounding words, take dependency syntax. Look at the head of the sentence the relation between the head and the named entity you're interested in, and the words that have a load, positive or negative. And look at the dependency relations. If Milka is the subject and the verb is neutral and the object is positive and it has no negation, then you are sure that you have a positive sentiment. Negation can be detected easy because it's a specific kind of dependency relation. And when you know that you have a direct object relation, then you know that this is an attribute of your named entity. So dependency syntax, when applied, can make tasks such as sentiment mining much more precise. And it can also avoid attaching a word which is either very close to your named entity as being related to it, or in the opposite, it can find a long-range relationship. So for example, in German, it happens often that a verb is very far away from its subject or its object. Well, dependency syntax will bridge these, and even though they are far away in the sentence, they will be connected by a single dependency relation. So somehow the dependency tree brings related parts of your sentence closer and makes it easier to find relations between them. And this book by Osborne, you will find in the bibliography, is dedicated to dependency grammars, and it says that there are more and more works showing that syntax dependencies are correlated to other kind of dependencies, like semantic dependencies, prosodic dependencies, psychological dependencies. And here is an example of another corpus for which we have the complete annotation of dependencies. It's the Quran. And here is an example, a single sentence from the Quran with the dependencies between words. And this is somehow a mixture between dependencies and constituencies, because here you have a constituent and you have a dependency, but most of them are typically dependencies. So here you have a verb, another verb, a dependency between those two verbs. This one is the head of the sentence, believe, and this is the subject. And here you have a conjunction and the wa between those two, and here you have dependencies of the verb. So believe in the unseen, establish the prayer, and so on. So, and you have at this address, you have the complete Quran with dependencies. So why do we need dependencies in the Quran? It's to make inferences, because the dependency, as we will see next time in our next lecture, is the step towards semantics. To obtain the meaning of a sentence according to the principle of compositionality, we need the meanings of individual words and the order of the words, and more than the order, the syntax structure of your sentence. And then from the meaning of individual words, you move towards the meaning of the sentence. And this will allow to do inference in the Quran and so on, and in any corpus. Here is a tool. It's about French. You have the same kind of tools for English, but in French it's more important because morphology is more complex. The verbs in French have many, many more forms than in English. It's called LEF, like the beer, but with 3 Fs, which means Lexique de forme fléchie du français, so lexicon of inflected, so derived and conjugated forms of French. And this resource will give you the possibilities for each word in order to build syntax trees. It will tell you that door is intransitive, so the only possibility is to combine it with a subject, while aimer can be either intransitive, il aime, j'aime, or je n'aime pas, or transitive with an object. And prendre will have a valency of 2. It needs a subject, an object, and an indirect object with preposition a. Or it can also be used with valency 1, je prends cette chose, or even with valency 0 as an intransitive, je prends. So this resource can improve processing by giving the lexical information needed, a bit like what we have saw in combinatorial categorical grammar, where we had different tags for each word, where these tags correspond to the information you have here. Okay, so I will stop now. Once again, I have 2 questions for you. Let me show you. I have placed the, I will change quickly the mode edition, and I will change the role on the role. It will look like when you connect. I have placed the questions at the end, questions asked to students. So for the 2 questions you answered last week until yesterday, I am giving you 2 documents. This one is a research paper on the Sapir-Whorf hypothesis. So if you are interested in this theory about the connection between the language we speak and the perception we have of the world, so it's a paper on that. And also a presentation from a conference last year, which is about Sapir-Whorf used in science fiction. So how science fiction authors have used this hypothesis in novel and many other things. And here are the new questions. And one of the 2 questions is about this book by Xu Bing, which is a book entirely written in pictograms. So we mentioned this, I don't know why it's not displayed correctly. Ah, here it is. So you see here you have the complete book. It's 128 pages only with pictograms. And the second question is taking 3 sentences from this book and asking you to describe, so first of all, to say whether, in your opinion, there is a syntax structure or not, and how this structure is given. So by which method the author of this book gives structure to his sentences. And if from these 3 sentences you don't see the meaning, here you have the complete book. So you can read the complete book to get a better idea of how he's using pictograms. So again, these are very interesting questions, and I would really appreciate getting more answers than just 13. At this moment, we have 23 participants, so it's me, Tian, and 21 among you. So please, would be nice to have 21 answers next week instead of 12 or 13. And these are interesting questions. Do you have any questions on what we have seen today? You can ask now, or you can also ask in the afternoon if you're hungry.